Our next speaker is Professor David Rubin, who's an assistant professor at the University of Hawaii in Mona. He has a talk presented called Evaluating and Optimizing the Roman Prism for the Supernova Survey. David, are you online?
Yep.
Okay. And if you'd like to share your screen, that would be wonderful. Thank you.
Sure. Okay, how's that?
That's perfect.
Okay. Oh, thanks. So thank you very much for having me out. So today I'll be talking about work that the SITs has been doing, evaluating the Prism for the supernova surveys, optimizing the supernova surveys, and I'll even throw in one slide on what we did to determine why the Prism should look something like it should. Excuse me, like it does. Okay, so why are we doing supernova spectroscopy, live supernova spectroscopy? So we can think of two sets of reasons, which I've separated into the categories here. So there's directly what you can do with just the supernovae observed with the Prism and also observed with the imager. And then there's the value of that sample to the larger sample of supernovae that are only observed in the imaging. So we can think of two categories. And then we can think about each of those two categories with redshift, supernova typing, and supernova subclassification. So getting redshifts and typing just on the Prism observed supernovae lets you do an early, fully self-contained cosmology analysis, which I'll show you, depending on your assumptions, might give you a figure of merit in the 200 to 400 range. So that's pretty exciting, and it would be Roman only plus ground-based supernovae for nearby supernovae. So if you think about the larger, more like 10,000 supernovae coming out of just the imaging, getting a subset of those observed with the Prism lets you get your photometric classifier trained over exactly the same redshift range, over the exact same sort of data. It lets you test and train your host galaxy association. So just because a supernova goes off on a galaxy doesn't mean that that's not a projection. This becomes a little bit more interesting, getting up to something like a couple % contamination when you're spanning the full redshift range of Roman. And then finally, you can do supernova subclassification. So this looks like it's interesting to reduce astrophysical systematics. And as I'll show, you can also, if the supernovae are doing something that you don't expect, you can recover that out of the Prism. Okay, so here's what the Prism parameters look like, spanning the wavelength range 0.75 to 1.8 microns, with a dispersion that varies with wavelength, but is around 100. So the entire purpose of the Prism, this obviously has a lot of wavelength overlap with the Prism, but the whole purpose is point source continuum spectroscopy. So in other words, spectroscopy of the supernovae. So the dispersion is several times lower, so that means the exposure times are several times smaller. Here's what the sensitivity looks like. So you're getting about 23.8 AB in 1 hour. That's not really what you want for distant supernovae, which are more like AB 25, 26. But what I'll show is that you can actually stack up, or even better, fully analyze the time series data that you get out of the Prism and get something useful. Let's take a look at that. So here I'm simulating a time series every 5 days, 5 days in the observer frame. And we're looking at what we get at a range of redshifts. And these supernovae were chosen, these specific supernovae were chosen out of the simulation to have exactly the median signal to noise of their time series. So half of them are going to be better, half of them are going to be worse, just depending on the luminosity and extinction of the supernova. Okay, so at redshift 1.1, things look great. You could not only classify that as a type 1a, you could securely subclassify it. So you could sort it into, it's a branch normal 1a, you can measure its silicon velocity. And this is stacking up within 5 rest frame days of max with blue, or within 10 rest frame days of max in orange. And stacking is probably not really the analysis you want to do here, but as a way to just show you what the time series look like, it's not bad. The spectral features do evolve, of course, with time. So things look great at redshift 1.1 with a 1 hour time series of 1 hour exposures. You go up to 1.3, they look a little worse. So here, you might call it a likely subclassification. So you were perhaps separating out different types of 1As at about 1 sigma. So you're going to need to do some sort of Bayesian analysis that will protect against Eddington bias there. But the data are fundamentally controlling what you want for subclassification. You'll just need to be a little careful with the analysis. Okay, going up to redshift 1.6, I would call that a likely classification of a type 1a supernova. The red silicon line is visible. Can't quite see the sulfur W, but this is definitely a type 1 and probably a type 1a. So your classification may not be 100% accurate at redshift 1.6, but it is still useful, and the sort of thing where with an appropriate Bayesian analysis, you can make use of that data. If you go up to redshift 2, I would call that a secure redshift and not that much else. So you can see the break in the UV. This is clearly a type 1 supernova, but not necessarily a type 1a, but it does have a secure redshift, as I'll show you. Here's what so this is another way to look at the time series. So this is looking at how much of your signal to noise you get in different rest frame phase windows. So the highest signal to noise spectrum has about 1/3 of your signal to noise, the whole time series. And that declines with redshift because your supernova lasts longer in the observer frame. And so if you're just picking out one spectrum, you're getting less and less information out of that single spectrum compared to the time series. You get about half the signal to noise of the total time series within 2.5 rest frame days of max, about 2/3 within 5 days, and something like 85% within 10 days. So really, you want a time series analysis to get all of the signal to noise out of the data. This actually, we've been doing some analyses with time series, but there are some analyses we can't do, like we can't put these into SNID to do classifications. More time series training data would be very useful here, but we also have to think more about our analysis tool. Here's what the supernova yields look like, and what I'm doing is I'm showing you 2 different versions of this. So the 2D host galaxy subtraction assumes that you're taking a √2 noise hit because you're going to have to subtract the host galaxy from only the same orientations. So you're taking those dispersed images and you're only subtracting the same orientations. The 3D host galaxy subtraction, which is still work in prep, will give you, it will use all of the data, make a full 3D model of the supernova and the sky around it, including the underlying galaxy light, and subtract that. So you're using all of the data instead of just one epoch taken with the same rotation angle offset in time. So you can see that boosts supernova yield significantly at fixed signal to noise, something like a factor of 50% to a factor of 2, depending on your cutoff. But generally speaking, you're getting thousands of live supernova measurements, and things are looking very good, even well above redshift 1.
David, you have about
so how
2
do we
minutes.
Thanks. So how do we optimize Prism parameters? So I just want to generically comment on some of the trades. So broader wavelength coverage meant greater spectral range, but lower signal to noise because of higher backgrounds. And in higher dispersion linearly translates into higher exposure times, but it reduces the systematic uncertainties, for example, if you don't know your line spread function, because you're over dispersing the supernovae. So if we do a full forward model simulation of a supernova, no spatially varying host galaxy light, but if we simulate the supernova with a forward model code, then we can put in an inaccurate line spread function and get our biases. So this is what set the dispersion of the prism roughly. Here we're seeing supernova redshifts. So you're getting, we're taking real supernova time series, degrading them to look like prism observations, and then fitting them with a template, a relatively fixed template. And so you can see that you're getting your redshifts back above a redshift of 2 for most of the supernovae. For supernova subclassification, we're using a range of spectral energy distribution models. So this one is NEMO 15. We're also using Sugar and some others. And so we're looking at how well you can constrain the different components of the supernova spectral variation as a function of redshift. This is showing the reconstruction of a missing component. So if you didn't know what you were looking for, would you be able to find it? And this is showing that with 100 supernovae around redshift 1 observed with the prism, you could actually find something in the spectral energy distribution that you didn't know about, and recover it to a smaller uncertainty than your statistical uncertainty.
David, just so you know, you're going into your question time right now.
Okay. I'll skip this slide, but this is looking at how much time you should put into the prism. So survey optimization, this is a very simple survey optimization procedure, but we're getting figures of merit in the 2 to 400 range, depending on your assumptions. The surveys, interestingly enough, look very similar, whether or not you, or irrespective of your assumptions. And so thank you. I'll conclude here.
And thank you very much, David, for your talk. If anybody has any questions, please feel free to type them in the chat or in the session 2 talk area on Slack. I'd also like to apologize to Philip there. I cut him off on his question time earlier. So again, if you have any questions for either of us as speakers, please use the chat or the Slack below, the Slack channel for session 2. And I don't see any questions on this end, but so I have one that I'd like to ask David. If
I think
okay.
there is, Rebecca, something for David from Ranga in the thread.
In the thread. Let me see if I can find that. I cannot see that, Lee, so if you'd like to say it, that would be
I can read it. It says, how much, so David, how much does PSF undersampling affect the systematic floor, either in the residuals when doing the 2D host galaxy subtraction or introducing spurious features in the spectrum?
That's a great question. So for the imaging, there is a bit of an impact that we see in the Z band. So Alexander Sakota and I wrote a paper simulating it, and we saw slightly suboptimal performance in the Z band, but okay performance in the Y, J, H, and F. For the Prism, there's good news and bad news there. The good news is we're not undersampled. The PSF width really is about 2 pixels. So we haven't been worrying about it so much, but I do simulate a 4-point dither at each epoch.
Okay, thank you very much. I do not see any other questions. Does anybody else? Okay, if not, then I'd like to thank our speaker again and then move on to our next talk,